Alright, so let's talk about the technique of U-substitution. I'll start out with well, not a partial proof, I guess, some kind of explanation. Um, so essentially, U-substitution is doing the chain rule backwards. Alright, so let's start by just talking about the chain rule. The derivative of g of u of x is dg du times du dx, where dg du is understood to be evaluated at u of x, of course. So it follows then, if you integrate both sides here, the integral of the composite is equal to the integral of the product of the derivative of the outside function with respect to the inside function times the derivative of the inside function with respect to x dx. All right. And of course, any two, if essentially by the definition of the indefinite integral, this is g again, right? Because if you differentiate g, you get the derivative of big G of u of x. Okay, so there you go. And this thing I underlined in red is U-substitution. So here, let me show you a direct example. Actually, this is very unnatural for me personally, but I'm just showing you to try to be a good citizen of the mathematical world here. So g of u is e to the u of x is x squared, right? Then g of u of x would be e to the x squared, all right? On the other hand, dg du times du dx would be e to the u times 2x, which would be e to the x squared times 2x. All right, chain rule, great. So what it means then is the integral of 2x e to the x squared dx is equal to e to the x squared plus a constant by what I've underlined in red up here, which is U-substitution. Now, if we always had to think through U-substitution in this way, I think it would be maybe not as useful a technique, but it turns out there's like a really slick notation which captures the content of this theorem with essentially symbol pushing. So which is good for us mere mortals. All right, so here we go. Basically, here's the same example, but I'm going to use the usual notation. What we do is we say u equals x squared, right? Then du is 2x dx. That's the differential, right? And so, making that substitution, this is du, and of course this is e to the u, so I get e to the u du. So I change this to an integral in u, right? And so that's e to the u plus a constant, right? But then we undo the substitution. That gives me e to the x squared plus a constant, and there you have it. That's U-substitution. But the reason that it works, of course, is the chain rule. But the implementation of it is that we have to figure out what a good substitution is and eliminate, rewrite the integrand in terms of u as well as the measure, the dx. All right. So, if you don't follow the proof, it probably won't hurt you. Let's see here. So let's go on. Example 2. Uh-oh, sadness. Example 2. Suppose we were going to integrate the square root of 1 plus 13x dx. All right, so what we do here is we go, aha, I'm going to make the thing inside the square root u, and I'm going to make the dx. Well, I can't make the dx anything. Once I make that u, I'm stuck with it, all right? So du is what? Well, if that's u, then du is equal to 13 dx. So this dx, right, I can rewrite dx is equal to du over 13. All right? So this is the integral of the square root of u times du over 13. Or in other words, 1/13th, the integral of u to the 1/2 du. All right? And then that is 1/13th. 1/2 plus 1 is 3/2, so that's 2/3. U to the 3/2 plus a constant. In other words, we have 2 over 39, and then 1 plus 13x to the 3/2 power plus a constant. And there it is. That is the integral. So, you know, obviously the question is largely, how on earth do you figure out what to make the u, and does this always work? And the answer to both of those questions is you have to practice. Another example. So let's see here, sine of x dx over 1 plus cosine squared x. Alright, so here what we're going to do is we're going to let u equal to cosine x. Alright, if I do that, then this is like 1 over 1 plus u squared, but I know that's an inverse tangent integral, right? So du is minus sine x dx. And, oh, I should turn the light. There we go. Integral of minus sine x dx. And so this is actually the integral of minus du, right? Over 1 plus u squared. And there you go. Minus inverse tangent of u plus a constant. Then undo the substitution. Minus inverse tangent of cosine x plus a constant. And there it is. That is the integral. Let's see here. Let me give me a second here. I got an old calculus book in front of me, and we'll flip over to some of his U-substitution problems. See if I can't find something. I always make up boring examples. Yay, a package. It's UPS guy. So example 4. Suppose we have, this is very, I mean, I shouldn't forget this example. The sine, I'll do sinh, I did sine already here. Sinh of 3x, let me do ax, alright. A could be 3, a is a constant, alright. So what I do is I let u equal to ax. Then du is a dx. And then dx is equal to du over a, right? So I can trade this for the integral of sinh of u times du over a. And then I get cosh of u divided by a plus a constant. So the answer, right? The answer then come on. The answer then would be 1 over a, the hyperbolic cosine of ax plus a constant. And that's how you do that. Of course, let's see here, moving on, let me do more examples. Example 5. I'm going to do these until we're bored. If I have the integral of 3x minus 1 to the 5th power dx, alright? What I'm going to do is I'm going to let u equal to 3x minus 1. So du is 3dx. So this is the integral of u to the 5th. And look at that, dx is what? Well, dx is equal to du over 3. You notice there's two things I'm doing every one of these substitutions. The one is trying to identify like what it is I want to make simpler. So like I know that u to the 5th function is simpler than the composite of 3x minus 1 to the 5th, right? So that motivates me to make that u. And then I have to take care of the dx, right? And whatever's left over from differentiating the u formula, I have to, I mean, if the u substitution works, then whatever's left over, I'll be able to massage into something manageable. Let's see here. I'll show you one that doesn't work next. U to the 5th du. Alright, so that is 1 integrate u to the 5th, get u to the 6th. So 1/18th, u to the 6th plus a constant, and lo and behold, the answer. 1/18th, 3x minus 1 to the 6th power plus a constant. So I try to write a little thought bubble over here, just to illustrate, where the U substitution came from. Now, in the context of Calc 2, right, there's certain U substitutions I'm not going to show my work for, and that's just otherwise it would be burdensome. For example, I'm not going to show my work when I do something like this. Sine of 2x plus e to the 3x minus e to the minus x plus the sinh of, x over 3. If I do something like this, I'm not going to write down my work. I'm just going to write 1/2 minus 1/2 cosine of 2x plus 1/3 e to the 3x plus e to the minus x plus 3 cosh of x over 3 plus a constant. Now, because this is a review, I'll be nice and I'll tell you what the U substitutions I just made are. It's really not that complicated. This was from u1 equal to 2x, u2 equal to 3x, u3 equal to minus x, u4 equal to x over 3. Those respectively gave me dx is du1 over 2, dx is du2 over 3, dx is minus du3, and last but not least, dx is equal to 3 du4. And so that's where this 1/2, this 1/3, this minus 1, and of course this 3 came from in that antiderivative. And you really want to be able to do it just like I did it, without thinking about the mechanics of this sort of thing. This needs to be hardwired, all right? Example 7. If I was going to integrate let's see here, how about, yes, how about x times the square root of x minus 3 dx. Alright. So again, there's a square root, right? So to make square roots kind of manageable, we like to make the thing inside the square root, the u, at this point at least. There will come a time when that's not quite the truth, but for now that's a good choice, u. And so if u is equal to x minus 3, then du is equal to dx, right? And here's one where it kind of doesn't work in some sense, like I was telling you about a second ago there. So we get x times the square root of u, right? And then du, dx is du. Oh no, there's an x left over. What do we do about that? Well, you don't just ignore it and pretend it's a constant and just say, oh, it's just the integral square root of u. Wishful but wrong thinking, don't do that. You have to do algebra. Now, it's not hard algebra, but it's algebra. So x is equal to u plus 3. Aha! And so, this is really the integral of u plus 3 times the square root of u du. And then, alright, so that's u to the 1, excuse me, 1 plus a half is 3/2 power, plus 3 u to the 1/2 power, right? Almost out of paper here, but 3/2 plus 1 is 5/2, so 2/5 u to the 5/2 plus, let's see here, 1/2 plus 1 is 3/2, 2/3, the 3's cancel, so I'm just left with 2 u to the 3/2. Now to check myself on that, you can differentiate this. That gives you 2/3. Excuse me, different derivative of this is 3/2 u to the 1/2. So the 3 and the 2 and the 2 cancel, give me 3. Okay, makes sense. Alright, so anyway, answer, 2/5 x minus 3 to the 5/2 plus twice the quantity x minus 3 to the 3/2 plus a constant, and that's how you do that. All right. So there's the answer. All right. Let me keep looking at this book here, see if I can't find some more examples for us. This is example 8. Let's see here. How about the integral of the secant of 4x times the tangent of 4x dx. Oops, x dx. What is that? Well, that's really the integral of secant of u, tangent of u, times what? Du over 4. If I let u equal to 4x, right? So then du is 4 dx, and dx is equal to du over 4. Anyway, so then that, of course, is nothing more than 1/4 secant of u plus a constant, or the answer, 1/4 secant of 4x plus a constant. All right. That wasn't too bad. Let's see here. Another example. Example 9. What if I was going to integrate the y over the square root of y plus 1 dy? All right. So, all right, I'm going to let u equal to what? Let u equal to y plus 1. So du is dy. So this would give me the integral of y, now dy would be du, over the square root of u. It's like, oh no, but I got a y left over. All right, so it's kind of that problem we just worked a second ago. This time y is equal to what? Well, y is equal to u minus 1 by algebra, right? So there we go. This is the integral of u minus 1 over the square root of u du, otherwise known as the integral of u to the 1/2 minus u to the minus 1/2 du. So that is 2/3 u to the 3/2 plus 2 u to the 1/2 plus a constant, and so the answer 2/3 y plus 1 to the 3/2 plus 2 y plus 1 to the 1/2 plus a constant. There you go. Now, so there's another example. Alright, let's see if I can find something a little bit more exciting. How about something involving square root? Example 10. The integral of, let's see here, how about 1 over the square root of x times the exponential of the square root of x dx? Aha. Well, this we can let u equal to the square root of x. That makes du dx over 2 times the square root of x, right? In other words, dx over the square root of x is nothing more than 2 du. So this, when I substitute, I can take this guy and that guy and make it 2 du. And I get e to the u times 2 du. Alright, so that gives me 2 e to the u plus a constant. And, sorry if I'm off screen, let me shift up a bit here. 2e to the u plus a constant, and of course then we can go back and unsubstitute. We have 2 times e to the square root of x plus a constant, and there you go. That is the answer. All right. Now I should show you some more notation here. Example 11. Suppose we face something like the integral of e to the sine of x times the cosine of x dx. There's a really slick notation that we can use for problems that involve U-substitution. Here it is. So this is e to the sine of x, right? Check it out. If u is equal to sine x, right? Then du is, what is it? Well, it's d of sine x, right? And so, of course, that's cosine x dx, right? So rather than writing du, I could just write d sine x in the place of cosine x dx. So d sine of x, right? So imagine yourself in a world where I hadn't written u equals sine x. I don't have to. I could write this directly without even writing u. And if I can do that such that everything in the expression is just in terms of sine x, then implicitly I understand I'm making a u substitution. Voila. So as you can see, if you want to be a calculus ninja, this is one of your skills, because it saves oodles of writing. And I don't know, kind of have to be a real meanie to take off points for somebody doing this if they're doing it with understanding. But I don't know, I might be mean someday. No, probably not. I mean, it depends on the instructions. If I tell you explicitly write the u and you don't explicitly write the u, well, I will be grumpy. Alright, anyway, silliness aside. Integral of, I like this so much, let's try it again, e to the x, the square root of 3 plus e to the x dx, right? Well, that's the integral of the square root of 3 plus e to the x times the derivative of the differential, right, of e to the x plus 3. Or I wrote it the opposite order, sorry. So the point is, basically I'm saying I can make u equals to e to the x plus 3, and then du, of course, is e to the x dx. So, you know, this is the integral of the square root function, which of course by now we know is 2/3 times the 3/2 function plus a constant. Example 13. What if I had the integral of, let's say, alright, what do I want here? The integral of secant squared 2x times the square root of, all square roots, man, so boring, tangent 2x, alright, dx. So let's see here, how could I do this? This is really 1/2 the integral of the square root of the tangent of 2x times the differential of tangent 2x. Alright, so that is 1/3, because the 2 and the 2/3 cancels. 1/3 tangent 2x parentheses 3/2 power plus a constant, bam. Sorry, I added a bam for good measure. Of course what I'm doing is just u equals to tangent 2x, right? So then du is equal to secant squared of 2x times 2 dx. So what that means then, of course, is that secant squared of 2x dx is actually equal to du over 2, right? And that's where this fancy schmancy 1/2 came from. All right. All right. I'm sure I'm missing some kind of example. Oh, there's a good example. I'll use that one. Example 14. You're like, but I don't really understand U-substitution. I was doing pretty well, and then the last part of the semester I just kind of glided by, and I never really fixed it, but I got a good grade anyway because I knew the other stuff really well, but I don't really understand U-substitution. Well, that is unfortunate. You need to fix that. Let's see here. Sine the nth power of sine a plus bx times the cosine of a plus bx dx. All right. So what we're going to do here is we're going to rewrite this as the integral of u to the n, right? No. Excuse me. First and foremost, all right, this is gonna be a two-stepper. All right, so it's our first two-step problem. All right, so sine of u to the n power, that's what this means, all right, times the cosine of u times du over b. What I'm doing is I'm letting u equal to ax plus b, a plus bx rather. That means that du is b dx, which means that dx is du over b, hence the division by b. All right. Now, suppose you have to make two substitutions. Clearly, your next substitution, it's like, I think any other letter other than this would just be wrong. Clearly, the next substitution is w. So w. I mean, it's a second u. So w, sorry, I'm stupid. W equals to sine of u, right? So dw is equal to cosine of u du, all right? And so that integral becomes, what is it? It is nothing more than w to the n. There's a 1 over b, I'll bring it out front. And cosine u to u is just dw. So there we go. That is 1 over b times n plus 1 times w to the n plus 1 plus a constant, right? Now, I need to unwrap that. So this is 1 over b times n plus 1. And let's see, w is actually equal to what? W is actually sine. So it's the n plus 1th sine. And then u was a plus bx plus a constant. And there you have it. Now, of course, this doesn't make sense for n equals to minus 1 for the division by 0 reason. But any other integer power, well, any other real number n, well, I don't know what that means. I mean, I guess we're assuming here that n is an element of the natural numbers. All right, fine. Let's say that. I mean, n's a count number. Number of fingers. I'm assuming you have at least one finger too. Okay, so there it is. Although this might still make sense. N equals 0. N equals 0. This would be the integral of cosine a plus bx, and yeah, it would still make sense in the n equals 0 case as it happens. All right. So I'm going to stop here because I'm getting a little bit tired. But next time I'll pick up with oodles and oodles and oodles of integrals of trig functions, which we must know. Thanks, guys.